Citadel Civil Engineering Department discussing Civil 203 Dynamics, learning objectives 4.3.3.2 and 4.4.4.2. In this case, what we're looking at is the plane motion of bar linkages. So this is from chapter 15 of our textbook from Beer and Johnson, discussing rigid body kinematics. And we've already learned a great deal about rigid body kinematics. We've talked about using superposition of translation and rotation to get the general plane motion kinematic properties of velocity and acceleration. We've also discussed using instantaneous center of rotation to turn velocity problems into fixed axis rotation problems, basically, by identifying the instantaneous center of rotation. We've also discussed non-slip surfaces such as gears and rolling wheels, and discussed how at the point of contact between the two objects, we'll get common tangential kinematic properties, meaning they'll share the same velocity and the tangential component of the acceleration. This allows us to write equations that will let us look at the motion of the two bodies and their dependence on one another. Today, we're continuing that dependent motion discussion and talking about bar linkages. So if we look at the bicycle frame suspension on the right, we can see a system with different members that are all pin connected. It allows for some motion, and the idea is that if we can know the motion at one pin, that we can then work our way to another pin and then onto a different object. And so we can work our way through the different bars in the linkage. Look at this. We can also, okay. So an example of a bar linkage like this is something like this, where you can see that I have pin connected members. There are 3 members here. They are pin connected. And where if I rotate one part of the system, the rest of the system will move. So it's kind of a cool little thing there. These would be fairly common in control systems on vehicles. Steering systems, mechanical steering systems would have been this way. Back in the day, before computer-aided drafting, we would have had a Leroy system where you would basically at one location using a 4-bar linkage, you would sketch a stencil, and on the other location on the 4-bar linkage, it would model the same motion, but using ink. So you could ink in your writing on a drawing, have it all look the same for everybody. So today what we're talking about, though, is this dependent motion. For bar linkages. The idea being that I might have 2 bars or objects that are connected by a pin. And so right here we've got our little pin connection. And at this pin connection, they're going to have common everything. So this will have common kinematic properties at pins. So the idea is that if by some kinematic work I'm able to identify, well, this pin is actually moving with a velocity like so by looking at the left member, then I can write similar equations for the right member that will have the same velocity at the pin. The same is true for the acceleration, whereas previously for a contact, a non-slipping contact, we would have had common accelerations in the tangential direction only. Now we have common acceleration for the whole pin. So it's only accelerating at one speed. So that's the idea, is that we have this velocity and acceleration, common kinematic properties at the pins. It's really pretty much as straightforward as that. We'll want to break our problems apart by pulling the pins, a little bit like frames, but we're not talking about forces anymore. Instead, we would draw our kinematic property diagrams, either fixed axis rotation, translation, or translation plus rotation for our general plane motion for each object, and know that the acceleration and velocity at each pin where they connect together has to be the same in both the diagram sets. So I look forward to working on an example problem with you in a little bit. Otherwise, this is it. Thanks.